So in our example, we're going to select 250 pounds of ferrous material as our mined experiment target. We know that we can get 1 nanotesla anomaly just purely from the induced field at 50 feet. This means that our survey grid could be 100-foot line spacings, 100 foot or 30 meters. And the reason is because the magnetometer sees in all directions. It sees omnidirectionally. So we will see out both sides 50 feet, a total of a 100-foot swath. So that means that we can, in fact, design our survey with 100-foot line spacings. The anomaly that we would expect to get from an object of 250 pounds or 100 kg out in the middle of the survey grid would be 1 nanotesla based on induced only. But in reality, we would expect to see a perm that would give us 3 to 5 times more than that. And if it was hollow, for instance, a ship or some sort of a case, or some sort of a ship's boiler, or something that actually had volume inside, we could see another 2 to 3 times that anomaly. So instead of being 1 nanotesla, it might be 3 times 2 is 6, and maybe it's a little bit longer. We could easily see a 10 nanotesla anomaly, which is very easy to detect, even given those other noise sources, such as wave noise, magnetotellurics, micropulsations, and electrojet noise. So we can see that not only does this inform our line spacing, but it also informs our toe depth. Because, as I said, the magnetometer is omnidirectional. And we are towing that magnetometer in the water column. So if we were to tow it higher than 30 meters, that would then inform our maximum detection range, because the magnetometers see out to the side, but of course they're also looking down. And if the sensor was more than 30 meters off the seafloor, then we might miss our target of 250 pounds in a most conservative sense. We would probably see it in this scenario if we had perm and also if it was slightly hollow. But this is to remind us that, that our altitude off the seafloor is also part of the equation. We do have on our website, under magnetometers, under marine magnetometers, under G882, there is an applet called Toe Depth. And Toe Depth is a program that will allow us to put in the type of magnetometer, in this case an 882, put in the type of cable, in this case a aramid fiber Vectran cable or Kevlar cable. It allows us to put in the tow speed and any additional downward weight that we would put on the fish. We do have weights that we can clamp onto the fish to give it a lower tow depth. But most of the depth is controlled by the tow speed and the amount of cable we have out, of course. So in some instances we may need to play more cable out. We may need to slow down in order to get the sensor lower. Another point to consider is that in general our tow cables are a maximum of about 400 feet that can be handled on a boat without a winch. So if we're going to have more, let's say, than 130 meters or more than 400 feet, then we would require a winch. And we have some various winch models available. Some are small boat operation, some are for much larger boats that are electrohydraulic and so forth. So this is just a brief overview of how we design a marine magnetometer survey, how we can find targets of various size given certain constraints about their materials, about the survey design, the logistics of our survey. All of this information is included in the applications manual for portable magnetometers, which is available for download off of our website under the literature section. If you have any questions about your survey or how to perform a survey, or would like more information about our marine magnetometers, you can contact us at sales@geometrics.com, and we would be happy to answer any questions you have about how the machines operate and what processes we use to make the final maps and get the answers you need. Thank you very much.